Morning, AP Stats. This is lesson 6.6, part 1, geometric distributions. So there's a bit of an elephant in the room. Remember that last lesson we had? We had the free throw shooter. That was, and he had to make 2 shots. What was it? 3 shots, he won the game. 2 shots was overtime. 1 shot, he lost. And so he kept shooting these free throws. And the problem is, you're probably thinking, you say, whoa, Mr. Smith, hang on there, right? In that last lesson, the guy shooting the free throws, by making or missing the free throw, wasn't he actively changing the free throw percentage? So in that case, the bins thing for binomial, part of this is that you have to be independent. And which means one event doesn't affect the other event. So by him making his free throw on the first time, didn't that make his free throw percentage just a little bit better for the second shot? And by him missing the second shot, didn't that make it a little bit worse for the third shot? All right, so it didn't really meet it in theory and technically. Yes, it was binary, meaning he missed it or made it, one or the other. Not necessarily independent, because the probabilities were affecting each other. There were a fixed number of trials, 3. And the probability of success did change. So it wasn't really binomial, but we still use binomial to do this problem. So here's a rule. It's called the 10% rule for independence. All right. Some say 5. So check it out. There's some arbitrary stuff in stats. That's different from calculus. But 10% rule. The accepted rule is that if the number in your trial divided by the total number in the population is less than 10%. All right. So that means if your n here is less than 10% of what is going on overall, then you can assume independence. That means that the probability isn't going to be affected too much. All right, no more than 10% of the population is sampled. That's what that means. So like in the free throw situation, he shot 3 free throws. So 3 free throws is probably less than 10% of all the free throws he shot. All right, so because it's such a small number compared to the overall population of the number of free throws, we go ahead and say that the probabilities probably weren't changing all that much. All right, so 10%. If n is less than 10% of the population, that's n divided by big N, so sample size versus population size, and little n versus big N. You can assume independence, and therefore the binomial distribution gives a good approximation to the probability distribution. All right, therefore, because the shooter had probably taken many free throws, we can assume independence. Go ahead and read that. And then the big question is, why 10%? Why is 10% the cutoff for assuming independence? Because that seems arbitrary, and it is arbitrary. Some statisticians do 5%. AP Stats does 10%. Some probably do less than 5%. All right. So anyway, the 10% rule for independence. If the population is less than, samples less than 10%, go ahead and assume independence, and you can continue with binomial distribution. So 60% of, for example, 60% of all computers sold by a large computer retailer are laptops, and 40% are desktop models. The type of computer purchased by each of the next 12 customers will be recorded. And define the random variable of interest as the number of laptops among these 12. All right, so is this binomial? So you have to work through your bins anytime you're asked Is it binomial? So is it binary? All right, so laptops. You're either buying a laptop or you're not buying a laptop. All right, so check. Independent. All right, so it says that 40% of the desktop models are laptops, and 60% are laptops and 40% are desktops. So this probability is assumed not to change regardless of how you pick. And we're going to assume that 12 divided by the total number of laptops is less than 10%. So that's a bit of an assumption right there, isn't it? But I'm assuming that overall this store is selling more than 120 computers overall for whatever their existence is. All right, so I am making a little assumption here that 12 in the realm of all computers sold is not very big. And so therefore, by looking at 12 laptops, that's not going to affect the probabilities. All right, so we'll give it a little check mark for that one because it's kind of there. N is 12 in this case. All right, and then the probability of a laptop was 60%. All right, so N is 12 and P is 0.60. All right, compute the mean and standard deviation of the binomial distribution. We have a formula for that now. That's just NP. So 12 times 0.6 is 7.2. So typically, you would see 7.2 laptops being purchased. That's the typical value. And then the standard deviation is the square root of N times P times Q. Some people say Q here. Whoops, I'm not even in the screen. N times P times Q, or Q is 1 minus P. It's the negation. So you end up with 12 times 6 times 0.4, and it's just 1.697. So typically we vary from the mean of 7.2 by 1.697 laptops. All right, so your typical day, you will have 7.2 plus or minus 1.697 laptops. That's what you would technically want to see in a day. All right, suppose we were not interested in the number of laptops purchased by the next 12 customers, but of the next customer, which of the next customer would be the first to purchase a laptop? All right, so you could do something like this. You could be like, they could buy a desktop, they could buy a desktop, they could buy a desktop, they could buy a laptop. Woohoo! They could buy a desktop, they could buy a desktop, they could buy a laptop. All right, they could buy a desktop, they could buy a laptop. What if they just bought a laptop right off the bat? Okay, so this is a different scenario. We don't have, in this scenario, we had 4 trials, we had 3 trials, 2 trials, 1 trial. This didn't have a fixed number of trials like we did here. This one we were always having 12 computers, and this one there could be 12 computers if they did desktop, 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 laptop, and on the 12th time it was a laptop. That could be 12, but it's not guaranteed to be 12. In fact, this would be highly unlikely that you'd be 12. More than likely, you'd probably draw maybe 1 before you get a laptop, maybe 2 before you get a laptop. So how do we run this probability? Well, this is called a geometric distribution. All right. So now we're going to play a little game called Greed to kind of work through what geometric is. All right, so go ahead. Each round, and if we were in class, we would do this by standing up on our desk. And it's kind of fun. I miss it. Each round, you must decide if you want to sit or stand. If you sit, you keep all earned points, but are no longer playing. If you stand, you must play the round. you can earn 1 point for each round you make it through. Mr. Smith is going to roll a die. The die lands on a number from 1 to 5. People standing move on to the next round. If the die lands on a 6, the people standing lose all of their points. All right, winner gets a 3% quiz bump. That's a bummer. All right, how many points did you earn? So we play this game, and then we're going to run the probability. So let X be the number of rounds played until a 6 occurs. Is this a binomial setting? Let's go through it. All right, so is it binomial? So let X be the round until a 6 occurs. So either a 6 is occurring or a 6 is not occurring. So it is binomial, binary. Is it independent? The probability of a 6 does not change from one roll to one roll. So it is independent. N. No. Is there a fixed number of trials? And this is no. No, not a fixed number of trials. You might get a 6 on the first roll. You might get a 6 on the second roll. You might roll the dice 10 times before you get a 6. So there's not a fixed number of trials. Is there a set probability of success? Yes. In this case, P is 1/6, because there is 1 out of 6 sixes. 1 out of 6 sides on a dice has a 6. All right, so use the probability rules to calculate the probability for each of the following. What's the probability that the first roll is a 6? That's just a 6. Okay. What's the probability that the second roll is a 6? That means that you did not roll a 6 on your first roll, and then on the second roll, you did roll a 6. So you did not roll a 6, and then you rolled a 6. So this ends up being 0.139. Okay, what's the probability that you roll a 3? You see the pattern? You did not roll a 6. Sorry, probability you rolled a 6 on the third time. Probability of not rolling a 6 times the probability of a 6. So not roll a 6, not roll a 6, and you rolled 6. Took you 3 times. Probability of a 4, of not rolling until the 4th time. See the pattern? And it goes down every time, right? Your probability is decreasing. The chances of rolling not a 6, not a 6, not a 6, and then a 6 ends up at this point, it's 10%. You have a 10% chance, roughly, of rolling a 6 after 4 tries. All right, so now let's generalize. This is what we do in math. We like to generalize this. So what if I want any number here? The equation looks something like this. It's going to be 5, 6 times 5, 6 times 5, 6 times 5, 6 times ... Until, so for 4, we had 3, 5, 6. For 3, we had 2, 5, 6. And then the last thing is going to be a 1/6, right? Just like here. So you got however many 5, 6 you need. All right, so what that ends up looking like is you take 5, 6 times k minus 1. And we'll let that be, as in, like for 4, you used 3, 5, 6. So that's 4 minus 1. That's why I put like a k minus 1 there. And then you finish it with a 1/6. All right, and then here's the overall formula for this, and this is what you'll see in your formula packet. You see 1 minus p, that's the 5, 6, that's 1 minus a 6. That's the, we call that q in some formulas, but it's 1 minus, it's the complement to the 1/6. X minus 1 times p. There's your formula. So this is a bunch of 5, 6 times 1/6. There's the formula. That's the probability finding. This is called a geometric distribution. Wish we could have played that in class. Maybe we'll do that. Hopefully we'll be together for like a review and we'll play it together. All right, so here are the probabilities of a geometric distribution. If you like to see how the formulas are come up with for this, like here's some formulas that we came up with together, just using a little intuition and probability. The probability of x equals x for that. This is a mess to get this formula. So this is one of those things where you just have to trust me, take my word for it. And same thing here, it's a mess. But if you want to see how these formulas are, we get to them, go click here. Okay, so a geometric distribution is defined as the following. X is the number of trials until the first success, so until the first 6 is observed. Probability distribution of X is called geometric. Trials are independent. Each trial can result in one of 2 possible outcomes, so it's binary. The probability of success is the same for all trials, so this does follow the bins, all except for n. Okay, so write the probability. Oh, and then these are your nice formulas. These are in your formula packet. Write the probability that a 6 is rolled with within the first 4 rolls in the terms of x, and find the probability. Show your work. So we're going back to that last roll. Probability that x doesn't have to be the 4th roll. We're saying it's within the first 4 rolls. So in this case, I'm going to write it like that. And the long way, so that's the probability that x is 1, plus the probability that x is 2, plus the probability that x is 3, plus the probability that x is 4. Just like that. And then you can go back to here and add all these up. And you get 0.518. So you have about a 50% chance of rolling a 6 in 4 or fewer rolls. There you go. Or there's a calculator. There's a calculator thing you can do. So get out your calculators, and we're going to go into this, and we can go into menu, probability, distributions. So at this point, we know about the binomial distribution, we know about a geometric distribution, and there's a normal distribution, which we'll learn about next. We have chi-squared distributions, t-distributions, binomial distribution, geometric distribution. If so, you remember when we did binomial, the PDF was like precisely. So if I want like precisely 4 rolls, I would do geometric PDF, and CDF is for like cumulative or accumulative. So that's what we want, geometric CDF. All right, it'll ask us for the probability of success. You can just type it in as 1/6. Lower bound is 1, and the upper bound was 4, just like that. And you can go ahead and press enter, and that's rolling at 1 time, rolling on the 2nd time, rolling on the 3rd time, rolling on the 4th time. So it should accumulate all of those probabilities, and you get the answer that we got right there. All right, so it's genome CDF. Like that. All right, how many rolls would you predict it take until a 6 is rolled? So on average, how many times do you have to roll until a 6 is rolled? All right, that is asking for the average, which is 1 over p. Now, intuitively, what is it? If the probability is 1/6, how many times before you roll a 6 would you expect? So plug that in, which is 6. You would expect within 6 rolls, you're going to get a 6. So that kind of intuitively makes sense for this. Within 6 rolls, you'll get a 6. So there's the formula. What shape would the distribution of x have? Now look at the probabilities. They start up at 16%. Then they go to 14, then 11, then 10, and they keep getting smaller and smaller and smaller. In fact, the geometric distribution is always going to start strong, and then it just kind of tapers off. Like that. It'll taper off. So the distribution, if you look at it, is always going to be skewed to the right. Always. The geometric distribution is always skewed right. Because you start strong probability of something happening, and then it gets less and less as you continue. All right, last example is example 3. Marty decides to keep placing a $1 bet on 15 in consecutive spins of a roulette wheel. Roulette is the one with the wheel with the green, 2 greens, and 18 reds and 18 blacks, I believe. That's what that is. So she wins. On any spin, there's a 1 in 38 chance that the ball will land in the 15 slot. Let T be the number of spins it takes until Marty wins. Wow, Marty's got a problem. He plays a $1 and she's placing $1 on 15. And hopefully 15 will get rolled. So show that T is a geometric distribution. All right, so what we can do is we can work through the bins. I'll do it this way. Is it binary? In this scenario, Marty either wins or loses. She either the ball lands on 15 or it does not land on 15. So in this scenario, yes. Is it independent? Ideally, unless the wheel is rigged, it would be independent. One roll, one spin of the wheel does not affect the other spin of the wheel. N. Is it a fixed number of trials? And no. We're looking at the number of trials until a win, which is not fixed. Could be the first try if she's lucky. And then S, there's 115 out of 38. So that's where we're going to use our S. Okay, next, find the probability that T is equal to 3. So this would mean on her third try, she gets the 15. And you could run this pretty quickly, like the probability that T is 3. Think about it. She did not get a 15. She did not get a 15. And she got a 15. 38. Why did I put 13 there? 38. All right. So run that out, or what that looks like is 1 minus 38 times 3 minus 1, and 1 over 38. So now I'm using, this is the formula that we got right here. Just plug it in. Just an example. And you end up at 0.025. Wow, she'd have to be pretty lucky. All right, so we'd say something like there's a 2.5% probability or a 0.025 probability that Marty wins for the first time on the third spin. Miss, win. How many spins do you expect it to take for Marty to win? This is an expected value question or an average question. So in this case, the average is just 1 over P, which is 1 over 38, which is 38. Takes 38 spins. All right. Would you be surprised if Marty won in 3 or fewer spins. Compute an appropriate probability. Okay, so that means the probability that the number of times is less than or equal to 3. Now I'm going to get out the old calculator and plug that in to geometric CDF, because we're accumulating. And I'm going to use 1 over 38, 1, and 3, which is 0.077, which is about 7.7%. Now, 7.7%. So you got 7.7% chance of spinning that 15. What do you think? Is that surprising, or does it happen by chance every now and then? Would you be surprised? And psychologically, humans are surprised when something happens if this number falls less than 5%. All right. And again, that's arbitrary as well. So if the probability of something falls less than 5%, then it's pretty unlikely. But if it's above 5%, then okay, sure, things happen by chance. All right, so am I surprised that if she won on the third try? No. I mean, I'm getting there. If she won on the second try, I'd probably be a little surprised. If she won on the third try, or within 3, no, probably not. All right. We call this being statistically significant. 7.7%, because 7.7% is greater than 5%, and like 5% is the magic number in our brain for some reason. Because 7.7% is greater than or equal to 5%, we say that 7.7% is not significantly significant. 7.7 is not statistically significant because it does not fall below 5%. Another arbitrary thing. There we have it. All right. So now what I'm going to do is we're going to cut it off there for today. And this homework will not be due next class. It will be due the class after. We're going to call it a part 1 and a part 2. Part 2 will be on Wednesday. You can do part 1 homework now if you don't want to get yourself all, stressed out. So I'm on quarantine now.